London, UK. Sugato Bose, with a bit of jet lag, but no, I'm quite excited to listen to your talk.
Okay. Thanks very much. Let me start by thanking Vladimir and the other organizers for inviting me here. I have slept 4 hours last night, so the talk might be a bit subdued. But so this is really 2 talks put into one. Okay, so there is one talk which is entanglement through spin chains, and the other talk is gates through scattering. Right. So rather than writing the 2 things, I put it this way. Okay. And the first thing, entanglement through spin chains, is something I have been speaking about for quite a while, and the results I'm going to present have also been presented for the last year. So some of you I actually see in the audience who have heard that part already. And the second part is newer, so I'm presenting them first time. Okay. So entanglement between well-separated individual spins is widely regarded as a very important resource in quantum information. Okay. Once you have 2 spins which are well separated by a distance and highly entangled, say almost in a singlet state, okay, then you can actually use it for teleportation, so you can connect up distant registers quantum mechanically, so it's a very valuable thing. And the angle that I will look at this problem is I'm going to try to see whether actually a spin chain, okay, a spin chain being defined as a permanently coupled array of qubits, okay, or actually could be also chain of spins, but the important thing is they are permanently coupled, their interactions are frozen in time, not changing with time, and whether they can serve to create entanglement between individual spins which are well separated. Okay. Once you can do that, then you can actually connect up to quantum registers, because you could send information from the spin in one of these registers to the others by using the process of teleportation and this entanglement. Okay. Why is this kind of thing, why would this be useful or interesting, is there are no actually physically flying qubits in this scenario. Okay. Usually people think of photons flying from one quantum register to another. People also think in ion traps, physically moving ions across, or shuttling electrons. Also there are a few ideas, but here there are no physically flying qubits. All are static, and it's the interaction which lets the information flow. The other aspect we are trying to emphasize here is that it's a low control method. We are not really trying to actually do anything active on the spins in the middle, okay, like modulating them or shining any lasers onto them or anything like that. So it's a low control and no flying qubit. So this is why if one could do that, it would be interesting. Okay. However, there's a problem that in the natural states of these spin states, such as in their ground and their thermal states, entanglement of this kind between 2 individual spins is notoriously short-ranged. Okay. One knows that actually inside spin chains there is a lot of entanglement. Okay. That is known for a while now. So Vladimir, and then also Enric and others, and also Calabrese-Riccardi, many people have looked at this problem, and people know that if you actually divide a spin chain into 2 halves, okay, then there can be a lot of entanglement with them, so that it even diverges at certain points called quantum phase transitions. However, what we want is entanglement in individual spins, and that is known to be notoriously short range. It is typically between nearest neighbors or next to nearest neighbors, but doesn't go much beyond that. Okay. So what we want is difficult to achieve. So how can one do that? Okay. So one could, if it's not there in the ground state or the thermal state, maybe perhaps one could look at non-equilibrium dynamics. Okay. It has been known for some time that there are some papers earlier which showed that that if you have a spin chain and you have a left block and a right block, then if you kind of induced quench dynamics, okay, then you could actually create a lot of entanglement in the left and the right half of the chain. Okay. We are going to try to see whether the same kind of technique applies also to distant individual spins. Okay. So the scenario we are going to start with is the following. We are going to start with the so-called nil state, okay, of a spin chain. This is very easy to engineer. You just have a very, if you have a very anisotropic antiferromagnet such as an ising, okay, its ground state will be up, down, up, down, up, down, up, down. Okay. That's the nil state. And of course, the end spins of such a nil state, the end spins I have drawn outside the chain are disentangled. One is specifically up, specifically also, both can specifically be down, depends on whether it's even or odd number chain. Now, what we are going to study is that we suddenly change the Hamiltonian of the chain globally. Okay? So this is where my point of low control arises. I'm not going to do individual control or tuning of any interactions between these spins. I'm just going to globally change the Hamiltonian, okay, to introduce, to make the interaction according to a different spin model, okay, which causes more exchange of the spins, okay, so it is almost the opposite of this Ising model. And then we are going to find that there's a substantial entanglement which dynamically builds up over time. Now, just this slide is to show that this is not a trivial problem, okay, to try to make entanglement between two individual distant spins is somewhat challenging, because what you require is not only that, for example, that this spin is down and that is up, when that is up, that is down, okay. You also require the rest of the spin chain is serving as an environment to these two spins. It's kind of entangled with this. So if these have to be same, okay. Only when these two things in these ellipses are the same, then these two extremal spins are disentangled from the rest of the chain and you have a high enough entanglement. And this is quite a difficult thing to ensure for the whole chain, that not only must they be in the right kinds of states for being entangled, but they must not be entangled with their environment. Okay? So through natural dynamics, this is something we have to try to attempt to ensure. Now, okay, so this is the model with which we play around. So we start with delta 1 equal to infinity. Initially delta is infinity, which means it's almost an Ising model. So the ground state is up, down, up, down, up, down, or down, up, down, up, down, up. We don't know which, so we take an equal mixture of these two nil states. Okay, and then we suddenly quench to delta equal to 0. Okay, this is what is called the XY model. Okay, just this part of the Hamiltonian, and then since this is not, neither of these are an eigenstate of this new Hamiltonian, the system starts to evolve with time. Okay, because we are suddenly making what was previously equal mixture of two different possible ground states. We suddenly change the Hamiltonian so that each of these are not an eigenstate, so they have to start evolving with time. That is what causes the non-equilibrium dynamics. Now, this is actually a very easy problem to solve, because people know that in this XY model, actually every spin up maps to the presence of a fermion, every spin down maps to an empty site, okay, apart from some other phase factors, and then one could very easily find the states of the two extremal spins with time. Just the hopping of fermions in the lattice. Okay, these are the hopping amplitudes from the ith side to the kth side. Okay. And then one finds that the state in arbitrary side has a significant contribution, small f, of a state up, down plus down, up between the ends, and this contribution 1 minus f of other things, which are both up or both down. Okay. These things, both up and both down, can never be coherent, because the kind of dynamics that we have, XY dynamics, really just exchanges things. So doesn't change the initial number of ups and downs. So obviously if you have two ups, their environment is different from what you have two downs, and different from the environment of this psi plus, the number of ups and downs in the rest of the chain. So only this part can actually give entanglement anyway. So our target is to make this f as high as possible. And we find that the process that we did, which is just not just doing this global quench of interactions, happens to create quite a high value for this fraction. Okay, For example, when you have chain lengths of say about 10, then with just with 3 copies of this thing you can create a very high, like 0.99 fidelity with the perfect singlet using some more local operations. The amount of entanglement in any case is quite high for that length. And actually it scales as a function which falls quite slowly with distance, okay, into the power minus 0.22 if you fit the curve. You see, we did this with a low control process. We didn't go out to one individual spin of the chain and try to flip it. We just did a global thing to the whole chain. If you did such a low control process like flipping a spin in the middle, you would actually get a much higher fall. You would get 10 to the power minus 1/3 in fact. Okay, so why do we have a larger value, larger fraction of this entangled state? Okay, it is because of a conspiracy. Okay, a very kind of fortuitous coincidence of things. As I told you, this every up is like a fermion sitting there. Is the presence of a fermion, every down is an empty site. So you can visualize the dynamics. The XY dynamics is simply the dynamics of these fermions hopping. So every fermion is hopping both left and rightwards, and there is this special time, okay, t/2, when a fermion exactly at the central site would reach both the ends with an equal amplitude. At that same time, a fermion starting towards the edges would have reflected ones, but they would also be roughly equal distance from the two ends. Okay. So all these different fermions contribute to being in either of the extremal ends at the same time, and this is what causes this probability of the psi plus state, up down plus down up to grow. Okay. We are also, if you, the kind of this up down state also has this nice thing that the number of fermions they cross while going to the other end is also same on both sides, so that you exactly have this state psi plus. Okay. However, as I showed, that it was decreasing with distance. The entanglement was decreasing with distance. So ideally, we would like a scheme which is distance independent. Okay? So that if you go to longer and longer chains, you still have this entanglement between the extremal end spins, up, down, plus down. How can we achieve this? There has been a proposal for some time by Campus Venuti and others, where people use extremely weak couplings. Okay? So if you use very weak couplings, then you can have effective interactions and things like that to generate entanglement between distant spins. But this is very non-robust to temperature, because you have to cool to the temperature lower than the coupling square by whatever there is a gap in the system. So it's a very low. So we are looking for a kind of thing where you do not need to lower couplings too much, but you still get a significant entanglement between the end spins. Okay. So we are going to study the following kind of model, okay, where we will do a quench actually. But for the moment, we study this kind of model. I'll take some time to introduce this model to you, where you have a uniformly coupled chain with nearest and next nearest neighbor interactions. So next nearest neighbor interaction is optional here, but that makes the thing richer. And then at the end spin is an impurity spin. By impurity spin, we mean that it's coupled by a coupling J dash slightly weaker. Okay. Now, this spin has been this kind of spin chain has been introduced for a while by Affleck and co-workers, and is called a Kondo spin chain. Okay. This impurity spin is screened by a block of spins, okay, which is called the Kondo, a block of spins of length called the Kondo length, okay, and it actually is supposed to form a singlet with them, okay, or that is what is believed to be true. And so the single spin under this model is supposed to be maximally entangled with a block of spins and not entangled with the rest. Okay. Now, how does one verify this? Before that, I should also say that happens only as long as the system is gapless. Okay. As soon as the system starts developing a gap which is above this value of J2.23, then this goes away. Okay. You do not have this Kondo length anymore. Okay. So this block of spins is called the Kondo cloud, and that actually screens this chain as long as it is a gapless system. So it kind of introduces a length scale in a gapless system. Okay. Now we want to find out this length, okay, from first principles. What should one do to find this length out? One should just compute the entanglement of this impurity spin with a block. Okay, so we take blocks of more and more increasing length, okay, and we find out when the entanglement becomes unity. Okay, so the maximum entanglement a single spin can have, equivalent to that of a singlet, where the block acts really like an individual spin, and that length will be the Kondo length. Afterwards, the remaining part of the chain will be merely disentangled from this impurity spin. Okay. Now, to actually do that, it does not anymore suffice to use the usual measures which are most popular say, at least in the condensed matter community. What has become most popular measure of entanglement is the von Neumann entropy. And we set our task as in computing the entanglement of an individual spin with the block. Okay? So we have to have a measure which acts for general arbitrary dimensional systems in mixed states. Okay? The von Neumann entropy as a measure between, say, entanglement of A and entanglement of B works when these two together form the whole system. But when they together do not form the whole system, then there is a complementary part, the environment. You have to use some other measure. And this is called the negativity. Okay? How is it done? You take the reduced density matrix of these two systems, A and B, and then you take a partial transposition of the system B only. Okay? And then you compute some eigenvalues and their modulus sum -1. This is a good measure of entanglement. So we are going to try to use this in this model. What we actually did is actually to compute the entanglement between the impurity spin and a distant block. Okay, that is because of the methodology we used, it proved easier to compute that. And that entanglement, if this block is here, say a very short block is 0, okay, then you make this block larger, it still doesn't grow till, and then as soon as this block is after a certain length, this entanglement starts growing. Okay, when it starts growing, that is the Kondo length. Okay, beyond that, the spins are not entangled with the impurity. Okay, so this is how one could determine this thing, Kondo length, in the system as a function of this. This Kondo length is known to be a function of the coupling of the impurity. Okay, this J dashed, the slightly weaker than normal coupling. So the weaker it gets, longer is the length. Okay, but it gets weaker in a very slow manner. So this is a plot of the Kondo length as a function of this J dashed, and we found that in the Kondo regime, in the gapless regime of the chain, it follows this nice law which is expected for a Kondo system. Okay, it scales with the coupling, this 1 by root J dashed. The other interesting thing we find that in the Kondo regime, the system is almost scale invariant up to this new length parameter. Okay, so suppose you make the system, the spin chain larger or even larger, then you just, if you also make your Kondo length larger accordingly, then you have the same system again. Okay. To make the Kondo length larger, what you do is you reduce the J dashed. So you make the chain even larger, you have to reduce the J dashed even more, and then this whole, every scaling of entanglement of the system as a function of length and everything depends only on the ratio of this Kondo length to other things. Okay. So it just becomes, you can just resize your system by tuning this J dashed parameter. Okay. This is what allows you to engineer for any length of chain the same spin chain. Okay, by accordingly reducing the J dashed. Now, this is an aside. This previous calculation that I told. So far, yeah.
How does the Kondo length exactly depend on J dash?
Yeah. So Kondo length depends on J dashed as 1 by logarithmic of so n. If n is the length, okay, then it depends 1 by logarithmic of n is the J dashed. Okay. So it is quite a good scaling actually. log 1 by log n scaling is not bad at all. Okay. Now, so one actually can write a simple structure for the ground state of this Kondo system based on these studies from this entanglement measure. There is this impurity spin up and down, okay, and it is entangled with a block of spins in the chain. But there is a part of the chain, okay, which is not entangled with this impurity, but it is actually entangled with the chain. Because if you look at the situation, okay, when you go very far, this block I told you is not entangled with this impurity. But then you can think that as a situation where the impurity is almost forgotten and this is part of a spin chain. And it's a gapless spin chain, so there is a huge amount of entanglement between its halves, this logarithmically diverging. So you cannot really ignore the entanglement between this and that part. This is why you have to come to a representation like this. This is the rest which is entangled with this chain. However, the impurity is only entangled with the block. So one can kind of, this negativity nonetheless allows you to kind of extract the structure for this kind of thing. Okay, now why did I do that? So we come back to our original mission, which was to try to use this to entangle, to generate entanglement in individual spins. But so far I have been talking about entanglement between one spin and the block of Kondo length. Okay, and you might be wondering that why I went there. Okay, because my target, what is useful in quantum information, is entanglement into individual spins, and I have been going on about entanglement of one spin with the block. Okay, but this is the trick. This entanglement of a one spin with a block can be converted to entanglement into individual spins if suddenly you do a single local quench at the other end. So what you do, matching with this J dashed, you also suddenly decrease the coupling of the spin at the other end of the chain. Okay. Now, normally the chain is in the ground state of this system. Okay. And if you suddenly quench this coupling, okay, then it is a non-eigenstate and it should start evolving again. So there is now non-equilibrium dynamics. And so this is more in equations what we do. We have the J2 just as a handle to switch off or switch on the Kondo cloud. Okay, whenever J2 is greater than this 0.3, the Kondo effect is gone, the Kondo cloud is gone. Whenever it is less than that, the Kondo cloud is there. And we just make a J dashed of the n and n minus 1 spins as well. And then this is the time evolution of the entanglement. Okay. You see, it rises with time. Blip, 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 okay. So the dynamics is a very nice oscillatory dynamics, in fact, of the entanglement between the opposite ends of the chain. On the other hand, if you switch off the Kondo cloud, okay, you make J2 larger than, so that there is a gap, then the dynamics is very dispersive. Okay. And it has a pretty good scaling with length. In the Kondo regime, that's the blue thing, okay, the entanglement goes to higher than, it's about a value of 0.6, higher than 0.6 for lengths of 40. Whereas if there is no Kondo cloud, it falls down very fast. Okay? And time is just linearly growing. Now, what are the general features we observe? When the Kondo cloud is too small, which means J dash is too large, so that the system has a very small Kondo cloud, then actually if you do this process, no entanglement is generated. Okay? If we do this process with a slightly larger Kondo cloud, so lowering J dash further, after it reaches the middle of the chain, crosses the middle of the chain, entanglement starts being generated. Okay? When it really touches the other end, then entanglement is most, it is optimal. And that is when you require this kind of J dashed, 1 by log of the length of the chain. Okay? Now, if you go to further, if you reduce J dash further, again it starts going down. Okay? So this is kind of an optimal value where the Kondo cloud exactly touches the other end of the chain, but not the last spin. Okay? That is when you have the best entanglement. And why is it? We don't have a very good explanation. So all these were done numerically using time-dependent emerging. But what we have found in the numerics is that, as you might have realized from the oscillatory dynamics, very few states are involved. And actually, it is only exactly two singlets which are involved in the dynamics. Both of these are singlets. The quench we are doing is a very symmetric quench in a Heisenberg isotropic chain. So nothing other than singlets can be involved due to the quench. But why there are exactly two singlets, two states taking part in this dynamics of this many body system is difficult to be sure before. But this is what we find, and that is exactly what gives the nice oscillatory dynamics. We would like a more cleaner explanation, but this is what we find. Now what is happening here is an instance of a very interesting thing, that in condensed matter systems, we, as I said before in the beginning, I emphasized there is entanglement in abundance, okay, entanglement everywhere around, okay, but it's not in its most useful form. Okay. In this particular case, it was entanglement of one spin with a block of spins, which was initially there, okay, the Kondo cloud. And as a result of our quench, this entanglement of this cloud went over to the single spin at the other end. So this is an example of conversion due to a quench of a useless entanglement to an useful entanglement. So we have kind of harnessed, tried to extract the entanglement which is there in a useless form to a useful form. Now how do we know? Someone might argue that is it really the entanglement of the Kondo cloud which is going over? How can we be sure of that? Okay, so this spin is entangled with the cloud supposedly, and which we found out from other things. Now how are we sure that it is the entanglement of this spin with the cloud is just that the cloud whose entanglement goes over to the other spin, and that nothing else is happening? Okay, so this check is done can be done in a very clever way. You just, at the time of the quench, when you reduce the coupling at the other end, okay, you just cut off this spin. You set J dash equal to 0 on this side. So this is like sending this spin to, say, Alpha Centauri or whatever. Okay, so this spin can never interact with that spin. So we, by this process, we eliminate any effective interactions between the ends. So we just set to 0 any effective interactions between the ends, so that now only the entanglement this spin had with this cloud is the only source which can make these two spins entangled. Okay, the only way is that this entanglement goes over to this individual spin, because we have just cut this off. Okay, when we start the dynamics. So by this way we can ensure that it is indeed the Kondo cloud whose entanglement goes over, and we see that when the Kondo cloud is not there, so in the gapped regime of the chain, the dimer regime of the chain, when the system is gapped, then entanglement falls very fast because we have completely set this coupling to 0. Okay? But when the system is gapless and has this Kondo cloud, the entanglement kind of reaches a saturation. Again, this is numeric, so we don't know, but it seems like this is distance independent. Okay, it is going towards a plateau. So this is one way of creating distant independent entanglement. Okay, now how much truly we can take this interpretation of the cloud. The whole cloud is here behaving like an individual spin. Okay, which is making its individual entanglement go over to an individual spin, a real individual spin at the other end. How literally can we take this picture? Yeah? To examine this, we considered a different process. But first, let us digress a bit and consider this very simple problem of 4 qubits, okay, or 4 spins. You have if you have two singlets, okay, and they were interacting by J1 dashed and J2 dashed, okay, and you set the intermediate coupling Jn to exactly J1 dashed plus J2 dashed. It's a toy problem you can do, 4-spin problem you can always solve. Then what happens is this, okay, these were entangled first, and then what will happen is this will become entangled with this, and this middle ones will get entangled. Okay, this can be just exactly solved. We try to generalize this problem in a huge, we just set these single spins to be Kondo clouds now. Okay, so we make these individual spins very large. So this is really to test whether this cloud is really behaving like an effective spin during the dynamics. And this intermediate coupling Jm, of course, we cannot use exactly the same formula, this plus this, so we put a general function before, okay, which we try to determine. And then we set a coupling Jm, and then we see whether entanglement develops between these extremal spins. So now the situation that this spin is entangled with this Kondo cloud here, this spin is entangled with this Kondo cloud here, and suddenly we have switched on the coupling between these two spin chains. Okay? And whether these two will behave like individual spins is what we try to examine in the dynamics. We solve the dynamics fully numerically, and we find that that is what is happening to a pretty good extent, a pretty high extent. So entanglement is reaching very high values, and actually even higher values for similar lengths than the previous scheme. When we were just quenching the opposite end of a chain, then if you remember, for chains of 40, we had entanglement of value like 0.75 or something, okay? 0.6, no, 0.75 something. But here we have entanglement nearly of 0.9, okay? Slightly lower than for lengths of 40. Okay, so this is two spin chains of length 20 each. And they are having the dynamics which is very similar to the dynamics of two spin singlets. So a many-body problem of one spin condo cloud, one spin another condo cloud is effectively behaving like a four-spin problem here. And not with any sort of perturbative couplings. These couplings are just logarithmically decreasing 1 by log n, so this is not no effective interactions or anything going on. This can be useful to make a interesting router for quantum information. So this is just a cartoon. You can connect any two spins by this middle coupling, and you can make, say, A entangled with D or B entangled with D according to which coupling you switch on. So it is more versatile than the previous scheme, because there you had no option but to quench the coupling at the other end of the chain. And unfortunately, if you tried to quench a spin elsewhere, it did not work. Okay. On the other hand, here you can really route information. Now I'm going over to the second part of my talk. So I would like to ask Yanis the time actually.
You have 20 more minutes.
20 more minutes. So that should be enough. Okay. So now we shift topic. We are becoming more ambitious. Okay. And also, so both more and less ambitious in different senses. So let me tell you. So we are not going to consider many-body systems, hence from this point. So we have few systems. Okay. On the other hand, we are going to consider a much more difficult task. So far we were considering the task of entangling two individual spins only. Okay, and that is already useful because that could be used to interface quantum registers over a distance by teleportation. But now we actually want to do quantum gates. We will assume that the qubits are encoded in simple things like single spins or something, so that we will assume that individual qubit rotations on these spins can be done. So individual qubit gates is not what we are going to focus on. We are going to focus on how to do in a low control way quantum gates between two qubit quantum gates. Okay, what is required for universal quantum computation is arbitrary single qubit gates. You must be able to do arbitrary operations on single qubits plus an entangling two qubit gate. So this is the second part, this entangling two qubit gate, which we will focus on how to do. Now the usual method which is done requires very precise control. Okay, I have shown separated qubits. These two straight lines are like the two levels of the qubit. Okay, and usual mechanism is you bring them together, hold them together for a fixed amount of time, which requires, I re-emphasize, a very precise control of the interaction time, and you take them back. Okay, and that accomplishes the gate. So it requires very good time control. We are going to examine a low control process, namely scattering. Okay, so scattering is a low control process. Okay, and for a while people have known that scattering can entangle. Okay, for example, at least these are the names I found, but there are lots of other work probably on generating entanglement from scattering. Okay. So in fact, you can have spin-independent scattering also entangle internal levels and things like that. So you can see all these things. Okay. However, we are demanding a quantum gate. Okay. So this is much more demanding than just trying to entangle. And why is it difficult? Because scattering amplitudes for different different outgoing momenta can strongly depend on the spin state. Okay. For example, if you had, so we are now, for the moment we have drawn non-identical distinguishable particles, say the yellow qubit and the blue qubit, okay, and when they are, say, when they are in the same state, for example, the down state, then for example you can consider that they really scatter off each other, okay, if their spins are, for example, down, both of their spins are down. But and these curves here are the amplitudes, the probability of the scattering in various directions. Okay, this is the Cartman depiction. However, suppose they were in opposite states, then maybe they just pass through. Okay, this is a Cartman. This is not necessarily what is happening in a particular case. So the problem is that scattering amplitudes for different momenta depends on these internal states. What is a quantum gate? A quantum gate is a unitary evolution, right? And you want the unitary evolution to happen only in your qubit space. So your qubit may be encoded in the internal degree of freedom of these particles, such as spin. Okay? So if you're scattering and scattering depending on the states of the qubits, you cannot obviously accomplish a quantum gate. So we want to go to a low control method rather than fixing times of interactions. We want to have particles at infinity, okay, and just scatter them and go away, okay, and you must have a gate, okay. But at the same time, we are demanding that you have a unitary evolution only on this internal subspace. So this is non-trivial. So I will first propose a solution where these are non-identical qubits, one stationary and one mobile. Okay? And you will see through that example to how much difficulty one has to go to get the gate. Okay? That is why it is really difficult will be emphasized by the next example. So we first considered this problem, okay, where you have an impurity sitting at a fixed place. Okay, impurity, so we call it an impurity spin. It is a spin, a static spin at a fixed place, and you have a mobile spin scattering from it. The Hamiltonian for the mobile spin is its kinetic energy plus a spin-spin interaction when it really sits over the static spin. When the positions of the mobile and the static spin coincide, then there's a delta function interaction, okay, sigma dot sigma. It's a spin-dependent interaction, okay, we are assuming here, okay, between the one. And the problem is that this thing, this small sigma, or sigma is the spin of this electron, capital S, this curly capital S is the spin of this impurity. This thing can actually be written in terms of the total spin of these two things. Okay? So if these two spins are forming a singlet, okay, there's one kind of transmission. If they're forming a triplet, there's another kind of transmission. So whether when this electron encounters this impurity, whether it's reflected back or transmitted, okay, depends on their total spin, right? So obviously you cannot get a quantum gate on just the spin degree of freedom, okay, when you include their spatial scattering, okay, in the problem. So as you see, depending on the total spin, this scattering can be, this Hamiltonian is different. Okay? So the solution that we found, okay, it's a simple solution, but it shows that how much trouble you have to go to generate. You have to generate an additional potential at a distance, say x naught, okay, as an extra barrier. Okay, this is a spin independent, just like a wall, okay, but not a hard wall. It has a height, gamma. Okay, it's a delta function, okay, at a fixed place. And when you have that, then say if you add that thing in the Hamiltonian, okay, then actually the electron scatters back and forth between this impurity spin and that barrier. And you can actually generate a quantum gate if you set the initial, if you choose the momenta of the initial electron accordingly. Okay, if this momenta is resonant with this distance, okay, then effectively these two potential can be combined to one potential, and that combined potential depends on this strength gamma and the strength which is happening due to the spin states of this mobile and static particle. Okay? So by carefully choosing this barrier height gamma, you can make both these to be the same. Typically when gamma by j is 1/4, then for the singlet, combined singlet state of this electron and the impurity, and the mobile electron and for the combined triplet state of this mobile electron and impurity is the same reflection and transmission amplitudes. Okay? So in that case, you can have a quantum gate. And the quantum gate generically is of this kind of form. Okay? When this condition is met, the condition of the previous slide is met, it has this kind of form. So by adjusting the strength of coupling and the density of states and the energy that you are sending the particle, carefully one can make it what is called a maximally entangling gate. Okay? That is kind of the square root of the swap gate. Okay? That is what you can generate by appropriately choosing the transmission. So when the electron is coming, the impurity is sitting, there is this additional barrier. If it is transmitted, you have some kind of gate. If it is reflected back, you also have something like a square root of swap gate, but slightly different phases. Okay? It's kind of the dagger. If you have U, when it's going, you have the U dagger when it's reflected. Okay? So it becomes a bit probabilistic. Okay? So you have to know whether the electron has come back to you or it has gone through, and depending on that, there is a different gate between the static and the flying qubit. So though we aimed for low control, there is something of a memory needed here. You have to have detectors which detect where the particle has gone without really measuring its spin to really be able to use it. Also, if you want to use it for something, so for example, we tried to see whether you could use this gate just for swapping off the state of the static qubit into the mobile qubit. Okay? So you can think of having our system with this extra potential and then having a very hard wall. So the particle has a square root of swap, comes back, has another square root of swap, and takes it away. Okay? But this is conditional on transmission and transmission. So its probability becomes half and half, 1/4. Okay? On the other hand, if it has transmission and then reflection, then the square root of swap is undone. Okay? So it's very difficult to utilize it for something profitable. There's a strong probability aspect. Though we are always having a gate, whether we have reflection or transmission, the gate is different. And it's very difficult to utilize it. You have to have the memory of where it is going. You want to ask something? Yeah?
I forget this notation of
it is the density of states at the energy of the particle. The energy at which you are sending the mobile spin. Now, we will again go to a brief aside. We will now report our latest work, which I am doing with Vladimir, on actually another way of clever way of doing gates, where actually all these problems are circumvented. You don't have this problem of reflection and transmissions. Okay, you always have a gate. However, before doing that, let me motivate the fact that doing quantum transformation entirely with flying qubits, where there are no static qubits at all in the problem, is also an interesting problem and is widely used. For example, with photons, it's the famous field of linear optics quantum computation. People have generalized it for electrons, though when you do it for electrons, which if you don't want to use you don't use their interaction, you actually have to use some charge measurements, which way measurements. And also people have tried to generalize it to bosonic atoms. So there the thing is you don't have static qubits, just do computation with flying qubits. Okay? But typically all of these do not use an interaction between the qubits. On the other hand, it is known in linear optics that if you use effective nonlinearities, weak nonlinearities, efficiencies can be enhanced. So we will just take the same paradigm of flying qubits, but we are going to just put interactions and see whether quantum gates can happen. But there are two other essential ingredients coming here. Okay? One is that we have to take these qubits to be identical, and the other is we have to take them confined in 1D. Okay? These are two crucial ingredients. When they are confined in 1D, then and they are identical particles, then you see their quantum indistinguishability makes reflection and transmission processes indistinguishable. Right? You cannot tell whether this minus k particle has actually gone through or whether this plus k particle has reflected back. Okay, it's the same picture. One minus k particle, one plus k particle. This could have happened by the reflection, the bouncing of this minus k when it meets the plus k, or actually the minus k going through and the plus k going through. Okay, so transmission and reflection are the same thing. And this is the main trick. When this happens of course because we are taking an elastic collision, we have this 1D constraint, which means that the momenta and energy conservation together means that momenta have to be exactly the same before and after. Okay. So this means you can actually now always have a quantum gate. Okay, a gate will always happen because the internal states of these qubits, because of this conservation of momentum energy, they always have the same plus k and minus k things. So their internal states never get mixed with spatial states. So whenever two things collide in one dimension, elastically you will have to have a quantum gate, okay, between these flying qubits. Now the question is, we have to look for useful ones. Okay, of course, and we know the useful ones are of this kind, where if you can entangle. For example, if you come with a up spin and a down spin, then you have a chance of them being the same and them being different. Okay, here, since these are identical particles, you have to label the qubits somehow, and we do it exactly how one labels photonic qubits. So we take the photon, or the particle, interacting particle moving leftwards as qubit A, moving rightwards as qubit B. Okay, so they are labeled by their momentum. Okay, even momentum magnitudes are fixed. So you can say really minus k is qubit A, plus k is qubit B. Okay. Now, where Vladimir's great expertise came to help actually, and this is how we stumbled upon this thing, is that people solve these kinds of systems. This is an exactly solvable model, the Bose-gas with delta interaction. The best presentation is in the book which has been referred to several times in this conference so far. Okay, and these phases were calculated by Yang in the 1960s. That if you have two bosons with the interaction which is a delta function of the position, so this is not a spin-dependent interaction anymore. We just not consider spinless particles. Okay, bosons. You have when their positions coincide, they have an interaction. Then if they are coming with P1 and P2 and their momenta are exchanged, then this is the phase you should put before it. Okay, this is the factor which you should put for it, so not the phase. Okay, this is the scattering matrix. This is the factor you should put, and this is like e to the power I, the phase. Okay, so if you have two bosons P1, P2, you become P2, P1. You have to give a e to the power I theta, and that e to the power this is a unit modulus complex number, where C is the strength of the interaction and P1 and P2 are the two momenta. Okay. So this can be regarded as an application of Bethe ansatz for quantum gates in a very fashionable language. But of course, you know, it's a delta function interaction of two particles, so one could also solve the delta scattering and find the same thing. But we happen to go upon it from trying to do something useful from Bethe ansatz in quantum information. Okay. Now, what happens? So consider first, let us consider two fermions. Okay. Now, when their spins are parallel, okay, then these two, and suppose they have delta interaction in space. So only when they are sitting on top of each other they would interact. But two fermions in the same spin state, because of the Pauli exclusion principle, would never sit on top of each other. Okay, so they will just pass through without scattering. They will just not see each other. Okay, and then there will be just an associated -1 phase. Okay, for the up and down states. However, when these fermions are anti-parallel, okay, then there are these two processes. Okay, so consider this spin in this qubit A to be up and this qubit B to be down. Okay, there's a chance that they will not scatter off, they will just be transmitted, not scatter off each other. That depends on their, so if their the moment of relative approach is high, much higher compared to the C, or proportion of that, they will not scatter. If the proportional to their momenta difference, they will go through. And that is this thing. The up remains up and the down remains down because they just go through. But the chance of them getting bounced back means that the up returns and the down returns. But by returning, the the B becomes the qubit A, right? Because they are IBK particles, the right moving is the qubit A. So that is the reflection coefficient to become down up. Okay? So these are the evolutions of the up down and down up. Okay? And if you choose the momenta difference of the approach of these two qubits to be about the same magnitude as the interaction strength, delta interaction strength C, then you can have these maximally entangling gates. Okay. I will perhaps skip over this other thing. If you had, so I should tell that these kinds of gates are nothing to not just specially for fermions, can also happen for bosons. We get very similar gates. Now, you can also have a clever encoding for spinless particles. Okay? So then you still encode qubits as left going and right going, but you encode the qubit states 0 and 1 as two different magnitudes of momentum. Lambda naught for 0 and lambda 1, say, faster for 1. So lambda 1, the fastest momenta state, corresponding to 1 must be much larger than this interaction strength, and 0 must be much lower than this interaction strength. If you set that and you have two qubits approaching each other, again you have quantum gates. This is called the control phase gate, which is a very useful maximally entangled gate. Okay? So you can have that with this different. So this you can use for bosons which do not have spinless, which do not have any internal structure. That's the end of the talk. I will just tell that I have spoke about two different things. One is to try to entangle two individual spins at the ends of the chain. The other thing, the scattering, particularly, I like myself most the last bit of the scattering work, where it can actually probably have good implications for realistic systems, where you could have perhaps trapped atoms which are very far. And the usual thing people think about is to try to interface them with light, detect the light or something to entangle them. But here you would just outcouple these trapped atoms to one-dimensional waveguides for atoms, which are now there. People have actually even created this 1D Bose gas with delta interactions. You just have two particles. And then you would have a gate, and then you would catch them in opposite traps. Okay? So you can have a distant gates where no photons are involved, but mobile atoms are involved. Okay? The catch, of course, is, which I realized just during the flight to come to the conference. I was trying to prepare the paper with Vladimir, that actually this delta interaction, when you want to have this delta interaction in a 1D thing, for real atomic gases confined to 1D, to have the delta interaction, you already require the interaction strength to be much larger than the difference of momentum. So this will actually give this will still give entangling gates, but of a lower magnitude. So we had this maximally entangled state when this matched with the C. So if it's lower than the C, it will partially entangle, and one may have to repeat it to generate maximally entangled. But nonetheless, it should still work. Thanks for your attention. So my collaborators have been my postdoc Abul Bayat and PhD student, former PhD student Hano Vitek, he's a postdoc now. And of course, external collaborators. Pasquale has been involved with Kondo work, and he will speak about some other work in his talk which we have also collaborated on. And of course, Vladimir is the collaborator on the scattering quantum gates work. That's all. Thanks very much for your attention.
Thank you guys for a very inspiring talk. Any questions?
So more a comment. So I wanted to point out that if you allow yourself to measure the states of the spins, and there are protocols which are quite efficient for creating long-distance entanglements.
That is true. That is
across a spin chain.
That is true. Yeah, yeah. This is what is called localizable entanglement, right? This is what maybe Enrique was referring to. Yeah. So in this AKLT state, yes, if you have access to the individual spins in the middle, then you can measure them. And if you collapse them all to a certain kind, depending on what strings you collapse to, you can create higher layer. So we are working under the constraint or restraint that you do not want to do anything to the intermediate ones. some technologies it may be easy to do it, so then this does
You
not
don't need
apply.
individual access in the sense of localized access, you can make a global measurement on all the intermediate ones
Right.
simultaneously, and it still works.
Okay, that would be interesting. Yeah, so global measurement, but not in, no information about the. So you mean it's just a coarse grain measurement?
Coarse grain measurement on all but the
Right.
two extreme spins.
That is interesting. I don't know about. So I know the local. I don't know this one. Yeah, I should.
2004.
Okay. Yeah, well, that is interesting. If you can, is this for only certain models or generally?
General, Heisenberg, XY, XZ.
Yeah. So that may be. I think that is probably physically possible to make some kind of global measurement. But one has to be careful not to touch those ones. Yeah.
Any more questions?
Yes.
So in the real system, in 1D, you also have harmonic track.
That's a very good. Yeah. That's a very nice question. So this is what I was planning to talk more with Francis Parana. So really, one has to for this last bit I have shown. To make a realistic setting, one has to consider this scattering in a harmonic setting. Now, to the extent that the harmonic thing is the frequency is very very low, this may be a good approximation. Yeah.
Yes, please.
Yeah.
Yes, on the opposite side question,
Right.
is from the viewpoint of the functional analysis, is the delta interaction. It is possible to additional phase is the problem by the Pavelo X naught is 2001. In that case, is so it just is from the I don't understand is the connection to sort of additional phase to your required phase with the scattering patterns.
Right. Can maybe I go back a few slides and
Yes.
you can tell me exactly what.
Yeah, in that case,
Mhm.
no. If
More
possible,
back-
so it's a spinless case.
Spinless. Okay. So that was the next.
I'm sorry.
This one was the
Yeah.
spin. So I went very fast
Yes.
over it. I did not.
Yes.
Yeah.
Pavelo X naught is consider just a delta potential to transmit and not reflection. In that case, this is from the viewpoint of the functional analysis, it's using the method of the self-jointness of the self-jointness operator of this system.
So, first there is no difference between reflection and transition because this is identical particles. And then operator is self-adjoint. I mean, the wave function, the eigenfunction is continuous at the point where the function sits, so it's well
Yes.
defined. It's like rigorously mathematical and self-adjoint operator in this system. I mean, at the delta prime, the derivative of that function, that's
Yes.
the problem. Well, the delta function is okay.
Okay, I see. Thank you so
I
much.
studied this, and I understand the question, and
Yes.
So I guess that.
Yes, thank you so much. Yes.
Are there any more questions, comments? So before we thank Sugata again, an announcement, the bus leaves at 6:30, so you have some time to think of an ask more questions.
maybe more questions.
Anything else?